So I'm just going to pick up from the previous recording. What I had done was I had described the, for a second time, I described the charging process for the capacitor, how the battery creates a potential difference, which using generalized symbols, I said the potential difference was the difference between the potential at the top of the battery, which I labeled V+, potential at the bottom of the battery, V-, and that potential difference creates an electric field. The electric field creates an electric force. That electric force drives charges from the top plate to the bottom plate. And as the charges move, they pass through the light bulb, causing the light bulb to light. But we noticed in an earlier recording where I actually showed you the light bulb lighting, that the light bulb started out bright and got dimmer and dimmer and dimmer and finally went out. And I explained that by pointing out that as the charging process occurs, yes, there's a potential difference created by the battery, but in addition, as the plates transfer more and more charge from the top to the bottom plate, a new potential difference, an additional potential difference starts developing between the two plates, but that has an opposite electric field, an opposite sign potential difference. And when the potential difference between the two plates, well, let me say it like this, as the potential difference between the two plates increases, the total potential difference of the battery plus that of the plates, that total potential difference gets smaller and smaller and smaller. That causes the flow of charge to get smaller and smaller and smaller, which causes the light bulb to get dimmer and dimmer and dimmer. Eventually, the flow of charge stops and the light bulb goes out. Okay? But it's a gradual thing. And then I said at the end of things, well, that means, therefore, that there is a maximum amount of charge that gets transferred. And then I wondered, is there a way we can calculate how much charge, what's the maximum amount of charge we can transfer? What's the maximum amount of charge we can store in the capacitor? And that's how we say it. And the answer is, oh, yes, definitely, but there is a way to calculate that. And that's what we're going to do now. All right, so I defined capital V to simply be the negative of the electric field that the battery creates between the plates times the distance that the net displacement that the charges undergo as they go from the top plate to the bottom plate. They go through a long journey, but ultimately they just end up at the bottom plate, so their net displacement is just the separation distance between the plates. And so the potential difference is related to that electric field through this expression here. Okay. And so, with all that said, I can start to answer the question, what's the maximum amount of charge that I can store, by pointing out that based on everything that I just told you, the maximum amount of charge that I can transfer, let's call that capital Q, is definitely determined by, or at least related to, the potential difference that the battery supplies. The bigger the battery, the more charge I should be able to store. Let me say this explicitly. Although what we're doing is we're transferring charge from one of the plates of the capacitor to the other plate of the capacitor, the common language that we use is we say we are charging the capacitor, or just as commonly we say we are storing charge in the capacitor. So I'm going to start using the more common terminology and say, what's the maximum charge we can store? Okay, but really, when I say store, I just mean rearranging the charge from the one plate to the other plate. Hopefully that's clear. Right, so the answer then, or at least the beginning of the answer, how much charge can we store in the capacitor is, now let's see, let Q equal maximum, and I'm going to emphasize maximum, the maximum amount of charge that we can store in a given capacitor. Pretty soon, well, am I? No, probably won't. I was thinking out loud. Right. The first thing we notice, and I just mentioned this, that the amount of charge we can store is proportional to the potential difference that the battery supplies. Remember, that's my V plus minus V minus. V sub plus minus V sub negative. V sub positive minus V sub negative is what I guess I should say. Okay, so the maximum amount of charge we can store depends on how big a battery we attach to the capacitor. Okay. We turn a proportionality into an equality by inserting a proportionality constant. So the amount of charge we can store is equal to some proportionality constant times V. Okay? So this, in fact, is the relationship. Now, nothing that I have said so far has made it clear that the amount of charge we can store depends only on the potential difference raised to the first power. But experimentally, we find out that that's the case. So, in other words, Q doesn't depend on the square of the potential of the battery or anything else like that. It's just the potential of the battery to the first power. Okay. Now, C is another proportionality constant. And like all proportionality constants in physics, it actually tells you something physical. It has a physical interpretation, carries physical information. In this particular case, C, well, first of all, second of all, maybe, C has a name. It is called the capacitance. Capacitance. It is a number that describes the capacitor itself. Specifically, as it will turn out, C carries information about how the capacitor was built, how big the plates are, how close the plates are to each other, the nature of the stuff that's between the two capacitor plates. Remember, I said that there's some sort of insulating material usually between the capacitor plates. The capacitor plates do not actually come into physical or electrical contact until you connect them to the battery. So anyway, C carries the information about the geometry of the capacitor, how the capacitor is built, the sizes, the shapes, separation distances of the capacitor plates, and then any insulating material that might be in the capacitor itself. And so the larger the capacitance of the capacitor, the more charge you can store for a given potential difference. Okay? The SI unit of capacitance is the farad. Well, first I'm going to give you the symbol. So the symbol for the SI unit is capital F, and as I just said, it is called the farad. It is named after the English physicist Michael Faraday, who described a lot of this stuff. Okay, so we say that a capacitor has so many farads of capacitance. The capacitor that I used in the demonstration, which I'm going over and getting right now, is an astonishingly, it's not going to sound like it, but it's an astonishingly large capacitance. And this thing here, which is what I used in the example a moment ago, as I said, has a capacitance of 1.0 farads. In fact, if you look, you might even be able to see that printed on there. And then if you also look, you'll see just above that, so 1.0F on the second line, if you can see that. And I don't know if you can, but anyway, and then just above that is a rating of 5.5 volts. The meaning of that 5.5 volts is, very briefly, the maximum potential difference that you should place across these capacitor pins. Otherwise, you're liable to damage the capacitor. But 1 farad is an absolutely enormous capacitance, and you typically only see that. There's only 2 places I've ever seen a 1 farad capacitor. The first one is, of course, in here here in the classroom because these are really good capacitances for teaching about capacitance and for doing labs. And in fact, you either do or you either will do or have already done some labs involving this particular capacitor, okay, or one equivalent to it. However, other capacitors of much smaller value are much more common in real circuits. And so here's another type of capacitor. We also have this one here at school, and it looks like this. On the outside, it looks really different than the other one I just showed you, but it still has 2 pins. And so even though the casing is very different, the internals are exactly the same, which is there's 2 metal plates inside, and each metal plate is connected to one of these pins, okay? And you connect the battery to one pin, you connect the other side of the battery to the other pin, that sets up a potential difference, and stores charge. Okay. So capacitors, there are capacitors that are quite literally microscopic. Typically, you'll find those in circuits of computers, motherboards, and computer memory and such things like that. The other place I've seen 1 farad capacitor that I was going to mention is for powering subwoofers in cars. And so if you hear a car goes by and they get their music going, they get the subwoofer and it's boom, 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 that noise, that subwoofer is being powered by a capacitor, not directly from the amplifier of the stereo. And I'll explain why either later in some recording or perhaps we'll talk about it in class. Anyway. Okay, so capacitance. More common values of capacitance for other real-life capacitors are more like 10 to the -6 capacitors, which is a microfarad, 10 to -9, which is a I don't know what's 10 to -9. I don't remember. A nanofarad, and 10 to the -12 is a picofarad. Okay. Okay. So this is the answer to my question. How much charge can you store in a capacitor? The answer is it depends, first of all, on how big a battery you attach to the capacitor in the form of V here. So this V in my previous example in that demonstration I did a while ago in a previous lecture was 3 volts. Bigger battery, more charge you can store in the given capacitor. However, again, it's not safe to put a bigger potential difference across the capacitor than it's designed to handle. You could damage the capacitor. The other thing, and the real thing for the punchline of this recording, it determines how much charge, what's the maximum amount of charge you can store in a capacitor. It depends on the properties of the capacitor, how the capacitor is constructed, and this constant C carries that information. Okay, but typically you never see or rarely ever see the details of where C comes from for a given capacitor. You're simply told the numeric value of C. You're told how many farads of capacitance a particular capacitor has, and then you design your circuit based off of that. And indeed, that smaller capacitor, if I can read it here, I think that's 640 microfarads is this little one. So much smaller capacitance. 640 times 10 to the -6 farads, 640 microfarads. It can hold a much smaller amount of charge than that other one that we had looked at. Okay, so what I want to do next is, I said just now that you rarely, if ever, see the details of where C comes from. Yeah, but rarely is not never. And now I'm going to give you a chance. And so in my next recording, I'm going to actually show you how you can actually calculate C for a given capacitor. And I will drive home the point that C, the value of C depends on the geometry and construction of the capacitor and not at all on what you do with the capacitor. That'll be next lecture.